Open up almost any modern language model, Llama, T5, the current wave, and you'll find a normalization layer running over and over, thousands of times per forward pass. For years, that layer was LayerNorm. But today, most of them quietly swapped in something leaner called RMSNorm from a paper by Zhang and Sennrich in 2019. It does less work per call, costs no accuracy, and that tiny saving adds up massively. Let's unpack why it won. The whole story is a comparison. So let's put the two normalizers directly against each other. LayerNorm juggles a couple of jobs to stabilize training. First, it recenters, subtracting the mean so the activations sit around 0. Then it rescales, dividing by the standard deviation so the spread is controlled. On top of that, it learns both a gain and a bias. It works well, but every one of those steps costs compute, and remember, it runs on every single layer thousands of times per pass. RMSNorm asks a sharp question. Do we actually need the recentering at all? Its answer is basically no. It keeps only the rescaling, dividing each activation by its root mean square, then multiplies by a learned gain. There is no mean subtraction and no bias term anywhere. Fewer operations, the same stabilizing effect, and the researchers showed the quality simply holds. Let's walk the actual computation one step at a time, so the simplicity is obvious. Start with the activation vector coming out of a layer, just a list of numbers for that one position in the sequence. This is precisely the same input LayerNorm would receive. Nothing special is done to it yet, and critically, we never once compute its mean. Next, measure the size of that vector using its root mean square. Square each number, average all those squares together, and take the square root of the result. That single value captures how large the activations are overall, which turns out to be really all the normalizer needs to know. Then divide the whole vector by that root mean square value. This pulls the activations to a consistent scale, no matter how big or small they came in, which is the part that actually keeps training stable across very deep networks. Notice we never touched the mean at any point, and it did not matter. Finally, multiply by a learned gain, one weight per feature, so the model can stretch each dimension back to whatever magnitude it prefers. No bias term is added at all, and that is the entire operation, start to finish, done with noticeably less arithmetic than LayerNorm needed. Distill it, and 3 points explain why RMSNorm took over. It drops mean subtraction entirely. The insight is that rescaling, not recentering, is what actually stabilizes the network, so removing the mean step costs nothing in quality. Fewer operations, so it runs faster. Skipping the mean and the bias means less math on a layer that fires constantly, and those savings compound across a deep model. It quietly became the default. Llama, T5, and most modern large language models ship RMSNorm precisely because it matches LayerNorm's accuracy while doing measurably less work on a layer that fires nonstop through every forward pass. All right, let's lock in the essentials. RMSNorm, from Zhang and Sennrich in 2019, is a simpler, faster stand-in for LayerNorm. LayerNorm both recenters and rescales activations, while RMSNorm keeps only the rescaling by the root mean square. Dropping means subtraction, and the bias means fewer operations per layer with no measurable loss in quality. That is why Llama, T5, and most modern large language models now default to it out of the box. If you like these small but load-bearing architecture details explained clearly, Standarity.com is built exactly for you. Catch you in the next one.